Hello guys, today I have this problem from leetcode, leetcode 239, sliding window maximum. In my previous session, we have already learned how to solve sliding window problem. I think this is a good opportunity today to apply that template and whatever we have learned so far to utilize that here. So you are given an array of integers nums. There is a sliding window of size k which is moving from the very left of the array to the very right. You can only see the k numbers in the window. Each time the sliding window moves right by one position, return the max sliding window. Each time the sliding window moves right by one position, return the max sliding window. Window position 1, 3, minus 1. Okay. So first 3 elements we have the max 3. Next 3 elements we have the max 3. Next 3 elements the max is 5. Yeah. So we are actually finding all the max for each window and we are adding to that result and returning them. So it's a matter of finding the max element out of these 3 elements. So finding a max element from given k elements can be done very easily by using a heap, right? Priority queue, right? I can clearly see that we can solve this problem using a max heap. So what I'll do, I'll just write this code using a max heap because it is very straightforward. We'll just use our template, what we learned so far, okay, and then we'll see if we can optimize that solution. Okay, so let me start. We are going to return a result array, right? And result array will be of size what? Int. If you see this, the array size will be actually n minus k plus 1. For example, here 1 2 3 4 5 6 7 8 elements are there. Okay, and the max, the result set, right, we are returning is of size 3 and 3 6. So which is 8 minus 3 plus 1 nums dot length minus k plus 1, right? I'll return the result. Okay, fine. We'll just run a for loop. Okay, int I equal to 0, I less than nums length, I plus plus. We can think of this I pointer as a AND window pointer. Okay, and let's take another pointer which will keep track of the start window pointer. Okay, so I'll say j equal to 0. Okay, fine. Now as I said, we are going to use a max heap, right? So let's define a max heap. Okay, q integer. Okay, I'll say pq equal to new priority queue. Okay, integer, and it is a max heap. That's why our comparator will be like this. Okay, b minus a, it will return b minus a. Okay, and this will return a priority queue. So if we remember the template, what we do, we actually add the elements to the structure, data structure, right? So I'll do pq dot I'll say offer, right? Offer what? Nums I. Okay, after this we'll just add a condition, right, depending on the type of window that we are dealing with, right? And here we are dealing with a fixed size sliding window problem, right? And for fixed size sliding window problem we have to use a if block. Okay, so let's write a if block. Okay, in the if block we are just going to check this size of the window. There is no other condition that we need to check here, so we'll just say I minus j equal to k minus 1. Okay, and actually I could have used pq dot size equal to k, but I don't want to use that because I want to stick to template that I have learned. Okay, after this I'll say pq dot pick will give me the max element, and I'm going to add it to my result set, right? So I'll say result equal to, right, here I'll say result j, right? This is good. After that we want to remove the element, right? But we don't want to remove the max element. What we want to remove, if you see this, we want to remove 1 here, 3 here. So we are actually removing the last element from the window, right, which is nothing but the jth element, right? So jth element we have to remove. So I'll say pq dot remove nums j. Okay, and after that we want to just move the window, right? So j plus plus. Okay, this can also be written like this, j plus plus here. Okay, that's it. Anything else we have to do? Actually we are done with handling the window, moving the window for a fixed size window, right? I don't think we have to do anything else. That's it. I think this should work. Yeah, let's run the code. Cool, accepted. Let's see example 2, right? So only one element is here. Let's go and see the test. 1 k equal to 1 and k equal to 1. Okay, it should return 1. Yeah, cool, accepted. Wow, it's taking time. So you see, time limit exceeded. You see, this is a hard problem. We can actually further optimize this. I will tell you in a moment how can we optimize it, but I still believe this particular solution can be accepted in many interviews. Okay, so let's see this particular explanation again. Okay, you see this 1 3 minus 1, out of these 3 elements 3 is max. That's good. Okay, next window is 3 minus 1 and 3, and here the max is still 3, did not change. Okay, now the next window minus 1, minus 3 and 5. So for this particular window, in this particular case, 5 is our max. Okay, 3 is out, right? For this window 5 3 6, we got max at 6. Okay, when we are adding a element to this window and that element is greater than the last max, then only we are changing. Otherwise we are not changing the element, right? So here also see, first was 3, next element did not change. Second was 5, next element did not change. Then 6 and then 7. And if you remember, in my previous session I have already done a problem for finding the next greater element, right, by using a monotonic stack. Here I am going to use a monotonic queue data structure. Why? Because actually if you see this particular window, we are actually adding new elements and also removing the older elements. Okay, so we need a way to see the max element easily, and of course we also want to get rid of unwanted elements easily, right? So if we use a monotonic queue here to solve this problem using a array queue, okay, it will be very easy for us. Okay, let's see this example 1 3 minus 1. Okay, so let's say the first element is 1. Okay, we pushed that element to the queue, so we added that element to the queue 1. Okay, and now we are going to insert another element to this queue. Okay, so 3. When I'm going to insert this 3 into this queue, you see, if I'll just enqueue this here, then we are going to break the order. Okay, and we don't want to do that. So what we can do in this particular case, when the element that we are going to insert, if this element is greater than 1, we should move this 3 up. So if we can maintain that order, then we can solve this. Yeah, what we can do here, we can actually remove this 1 and we'll push this 3 up, right? Yeah, so let's do that. Okay, so how will I do this? Okay, I'll say I'll just create another queue. Okay, I'll just create another queue here. Okay, and we throw this 1 out and we'll have this 3 here. Okay, let's see what happens. Okay, so now 3 is the head, right? Okay, now let's now the next element is minus 1, right? So we can insert the element, we can actually enqueue the element minus 1, not a problem. Okay, now minus 3 is again smaller, this smaller than minus 1, so we'll add minus 3 also, that's also not problem. Okay, now let's see if we can insert 5. Okay, so now what I can do, I can actually remove all the elements which are smaller than 5, right? Or I can say, because 5 is greater than minus 3, so I'll remove minus 3 and try to put it here. Again, minus 1 is still less than 5, or 5 is greater than minus 1, so I'll just remove minus 1 and I'll try to put it here. Keep checking all the elements which are actually smaller than 5, we'll kick them out and we'll put 5 in its correct position. Okay, after this particular operation, what I will have, this queue will look like this, so I'll have 5. Okay, and now the next element is 3. 3 is fine, I can put it here. Okay, and now I'll try to put 6 here. So if I'll put 6, then again they are breaking the order, right? So I cannot put it. What I'll do, I'll remove all the elements which are smaller than 6. Okay, and I'll put this 6 in front, right? Now the queue will have again only one element, which is 6. After removing 5 and 3, now I'll put 7. So 7, again the same problem, they are actually breaking the order, so I'll remove 6 and I'll put 7. Now again after removing 6, we'll have 7 in this queue, right? So you see, by following a simple rule, okay, we actually could follow the monotonicity of the queue. So what we did, if you see this offer, right, while inserting an element to the queue, we will remove all the elements which are smaller than the element, right, and we'll make sure that it goes to its proper position, right. So that's what will change in this offer method, okay. And when we remove, what we did, if you look at this particular case, right, so as long as the element is not the max element, it doesn't matter if you remove it or not. So what we can do, this pq.remove, we will remove only when it is a max element, okay. So the number that we are actually going to remove is matching with the max element, then only we'll remove, otherwise we don't care, okay. So with these two modifications, actually we can build this monotonic queue. That's why I wrote this particular code, so that we can easily modify that, and instead of priority queue, we'll say it monotonic queue and solve this problem, okay. I hope it is clear. I tried to make it little more clear by using this particular tool. So yeah, let me know if you find it difficult to follow, but I think if we write the code, it will be more clear. So let me just wipe this and start coding. As I said, I'm going to use a monotonic queue, so I'll create a class called monotonic queue, okay, and I'm going to use a DQ, array DQ data structure, right. So I'll say DQ of integer, right. I'll say DQ equal to new array DQ, okay, and we want to define our new offer method, okay. So I'll say void offer anyway, I don't want to return anything, so I'll say offer, it will take an element int num, right. And what we did here, we made sure that the elements which are in front of this particular element, if they are smaller than this element, right, then we are going to remove them, okay, and that's how we are going to maintain the monotonicity, right. So what we do, while num is greater than dq dot get last, right. So that's what I did, okay. I could have actually kept that queue image here and it would be little more clear, but sorry, I have already removed them. So I'll say while num greater than get last, then what we want to do, we want to remove the elements from the queue, right. So we want to say dq dot remove last, okay, remove last, and we want to make sure that dq is not empty and num is greater than get last, then remove the last element, okay. And after that, when we find the correct spot, we just want to add this to our dq dot add last, okay, L capital, fine, okay. Now we want to remove the element, so I could actually write like this, void remove, right, override this remove like this, int num. If this num is the greatest element, then only I want to remove. So I'll say if num equal to dq dot pick. So if num is equal to the pick element, then only you remove this. And so I can say dq dot poll actually, right. I don't have to say remove again. So let me just actually I'll name this method to poll also, okay. And yeah, so we want to remove the element only when it is the pick element, okay. So otherwise it doesn't matter, right, they are already in the order, so it doesn't matter, it will be taken care by this offer method, okay. Anything else that we want to add here? Actually not, but I would still want to make it little more clear, so I'll write a max method, okay. I'll say int max, where I'll say dq dot pick, okay. And instead of calling this pq dot pick, I'll actually call this max method. Okay, so we have a monotonic queue data structure here. We have all the methods that we want to use in this particular problem. Okay, now what will I do? I'll just use monotonic queue instead of priority queue. Return. Now run the code. This is good. Now submit this code. Cool. So time complexity for this particular solution is O of n, because we are actually using monotonic queue here. Okay, you see how I change the priority queue into monotonic queue without changing the logic, the template that we learned, right, for solving any sliding window problem, right? Yeah, that's it for today, guys. Okay, and see you next time. Till then, bye, take care.